I was intrigued when Mike came and asked me to do this because, as many of you will know, I've spent most of my life designing homogeneous multicores, and there are some fairly good reasons for that, which I'll try and explain to you. He also had a bit of a discussion about history of this stuff, because it's probably my fault, because I do teach quite a lot of computer history these days to try and get students to understand why we do things the way we do, and that often it isn't particularly good. There isn't a good reason for it other than a political one or a commercial one rather than a technical one. So I was thinking about the history of computing and the history of parallelism and the history of heterogeneous processing. And actually, we've been doing this for an awful long time. And we've been doing it primarily, I think, for three reasons. One of the things that was pretty obvious way back in the early history of computing is that when you start making big processors to produce high throughput, they tend not to be very good at doing I/O. So we started surrounding them with input-output processors to do things that were much more agile. And you can still see that problem around today. I'll mention one or two examples. The other thing that we've done over the years is adding specialized acceleration. And one of the more obvious places where that's happened over 30 or 40 years is in computer graphics, and it's still the same thing. And we've also dabbled in building so-called general-purpose parallel computers, and you can argue at length about what general-purpose means here. And in some cases, in trying to push the performance of them as far as possible, we've been tempted to put interesting bits of acceleration in, which seems to in many ways make them somewhat less general-purpose. And that debate is obviously still going on as we see the attempts to push general graphics processors and other things into high-performance computing. So most of these things that have actually involved heterogeneity have often involved quite a lot of processors, not just the odd one or two. Although there are obviously examples where it's a processor and another different one. So there's the input-output processor and its history, as far as I know it, roughly. The IBM 360 was one of the pioneers here, and it had this thing called the channel. And the channel was a specialized processor that sat alongside the main processor and handled lots of the I/O. It was followed fairly rapidly by a supercomputer. It's pretty obvious why a vector supercomputer isn't very good at I/O. It was surrounded fairly quickly in its original design with 8 input-output processors that were all independently programmable to perform I/O operations. And now we have the ARM as the modern example of all this. And I was scratching my head for a while trying to figure out whether a chip with several arms, different arms, was heterogeneous or homogeneous. You could argue that it's fairly heterogeneous, given that it takes a 1,000-page manual to describe all the variants. But anyway, one interesting point about that is that the IBM 360 was actually one architecture with many different variants. It was designed to be like that, and as you will see, I believe this is a fundamentally very good approach. One architecture means one set of programming languages and tools, done in such a way that you can derive many different optimizations in the implementation. This is a very different approach from having multiple architectures, each presenting its own view and programming image to the user. So that's I/O. The specialized accelerators, I trace back to things like the ILIAC 3. The ILIAC 4, which we'll come on to in a minute, was a rather well-known machine at the time I was a student, roughly, back in the 1960s. It was preceded by the ILIAC 1, 2, and 3. And the University of Illinois had these projects, and they were particularly focused, in many cases, on various forms of high-performance processing, graphics, pattern recognition was what the ILIAC 3 was for. Some of those early machines were actually even the first machines that were applied to composing music automatically. Music wasn't very good to listen to, but at least it showed that computers could potentially compose things. So the ILIAC 3 unfortunately was destroyed in a fire when a large transformer on a bench caught fire and burned the whole thing down. So it was then resulted in the launch of the next generation, which I'll mention in a minute. Now, of course, we've also had attached numeric processors. That's always been a good line for a while. People were floating point systems, you may remember, some of you if you're old enough, attaching high-performance numerics to mainframe computers, or mini-computers in particular. And those carry on fairly successfully until the performance of the main CPU takes over and the companies get wiped out. Okay. That's what's happened more or less to floating point systems. Of course, graphics enters pretty early into all this. Evans and Sutherland, well known for their pioneering work on computer graphics and in particular high-performance simulation, rendering pipelines and so on, dating back to the 1960s, I guess. Ivan Sutherland, of course, who's still around, pioneered a lot of this work, including head-mounted displays and things, a long time ago. I noticed the company is still around doing high-performance systems for entertainment and things these days, so they've obviously survived over the years. So they particularly pioneered pipelines at the time that a graphics pipeline was a row of computers, with specialized hardware in a big room. And that kind of work followed through into the work of pixel planes and so on, which are more specialized processing technology for computer graphics. And I became fairly interested in some of this stuff when we started doing transputers and encountered this thing called RenderMan and the Rays machine, which there is a little bit of history about, which I'm going to tell you in a minute. Because it actually has a connection with Bristol. Of course, we've also had a lot of processor-co-processor combinations these days where you've got DSP or graphics accompanied by an applications processor. So the link with the RenderMan thing, which is a sort of interesting example. In case you don't know what RenderMan is, if you actually go and watch any animated movie these days, watch it through to the credits, you'll find that there is an acknowledgement to RenderMan. RenderMan is the software system that Pixar developed before they realized that the business they should be in was making movies. They started off attempting to make hardware to support graphics and rendering. And that was when I encountered them in 1987, as far as I remember. Now, there is actually a history that's been told of this in the appendix to a book that was published recently called Advanced RenderMan, and this is how it goes. The Rays machine was an expensive piece of hardware with a series of special-purpose boards that each accomplished one part of the Rays rendering pipeline. Most were programmable to a certain extent, and the first of these to proceed to a working prototype was the filtering pixel reconstruction board, which was a parallel array of transfuture processors. The transfuture was a CPU designed in the UK in the late 1980s, which had extremely high floating point performance and had parallelism and message passing hardware built into the chip, brackets quite unique at the time. We'll return to RenderMan in a minute. And then, as I said, the general purpose. The ILIAC 4 was the successor to the ILIAC 3. It was, as far as I remember, 4 quadrants of SIMD processors, 256 in all, they were meant to be. I'm not sure they ever built the whole machine. It was quite large, many meters long. And it was there to do SIMD processing alongside a general-purpose processor, and the general-purpose processor was the Morris B6000 series machine, one of the early stat machines. So that is a classic combination of the sort of general-purpose applications processor along with a fairly substantial, at the time, SIMD array for doing stuff like graphics and VSP and whatever else. So that's back in the 1960s, the very early 70s. Of course, around the same time, we get the appearance of things like vector processors, the CDC and the Cray. I don't know whether you can call these things general purpose or not, actually. They're sort of halfway between. The thing that really strikes me about this hardware is that the one thing that made the Cray successful was the fact that it was the fastest general purpose scalar processor in the world. Okay. It wiped the floor with all the other supercomputers at the time because it ran general purpose sequential code very well, and occasionally it could burst up to very high speeds with its vector processing. Okay. There were at the time numerous parallel machines that claimed to be general purpose high performance computers, which were very fast provided they'd run stuff in parallel, and slow if they wouldn't, and they just disappeared when these machines appeared. Now, there's another machine that was floating around, which is the same general idea, the distributed array processor. That's British. It was supplied as an attached processor to the 2900 series by ICL. It was a SIMD machine, and there were some people who found this quite useful. And then, of course, more recently, we've had SIMD making an appearance within general-purpose processors, early 90s. Some visual instruction set, the Intel MMX, and closer to home, the ST Chameleon project, which never actually turned into a shipped product, but probably generated quite a lot of technology, which has helped since then. And of course, we've also seen quite a lot of scalar vector nodes for HPC. This was one of the things that happened in the 1980s, in particular, when people tried to build these parallel machines. They decided to try and speed up the individual nodes by making hybrid nodes. This was usually not a good idea, because what happened was that the node was much too fast for the interconnection technology, and they're very difficult to use, these machines. Finally, I'm going to return to Enderman because there's an interesting end to the little story I told you about a few minutes ago. Thank you. It was not long before the team realized that the filter board design was so general and the transfuter CPU so powerful that the entire software array's implementation could be run on the transfuter array, creating a rendering machine that was significantly cheaper than the original array's machine design. Thus was born the RM1 project, a single board implementation of the array's machine. So you see, interestingly enough, they started off thinking they were going to build a machine with lots of heterogeneous components, and then they discovered that a better idea would be to build it as a homogeneous machine, just programmed to do the various different components. I will just complete the story so you understand where the Enderman word came from and how it comes to be the name for the software package. At some point during the design and building of the RM1, Pat and Jeff noted that one day the transfuter would be so powerful that a single chip would do the work of the entire arrays machine it was originally designed to do. You could imagine a small box with a single CPU and some super high density memory running arrays. It would render in real time and generate video you'd pipe directly into video eyeglasses. It would be small enough to carry around on your belt the way you carry a Sony Walkman. It would be a RenderMan. Well, we're nearly there. So I think it's quite interesting to see that the way in which this interplay happens. You know, you get situations where you put a specialized hardware together. You think you're going to need specialized hardware and diversification, and then you realize that actually a suitably general purpose parallel machine in particular can be used to program the whole thing. It's all software and it's all homogeneous. There you are. There's the religion. So. The last 20 years, what's been going on? People often ask me this, particularly when they notice that lots of papers and publications that come from the late 1980s seem to be as relevant today as they were then. We've now actually known... Hello? What should I do? Sorry? Is that better? Okay. How? I shall cover the screen up. It's good. Thank you. Okay. Right. Well, let's have a go. So we have known how to do general purpose processing for a long time. We seem to have forgotten a lot of the things we learned how to do in the 1980s and early 90s. And anyway, what happened was there was an explosive growth in PCs and things which actually took us all up in a different direction. And we came up with this idea that we should be following Moore's law, actually. It would be more correct to say we decided to implement Moore's law. It's actually pretty obvious. It's only possible with a very, very rapid and huge market growth because it's just extremely expensive. So it's a decision to go down that way. Fortunately, for people who want to go down that direction, loud microphone level, check the audio gain meters. I may need to reduce the mic level or move slightly away from the mic. How do I do that? It's attached to it.
If you move back a bit.
It's all right for me.
Yeah,
okay.
I'm still whistling.
I'm whistling. It's whistling. Well, it's not me.
They're right.
It's better here. Yeah. Right? Sure? Let's try again. Where would you like me?
I think that's it.
Let's try again. Okay. So there has been very rapid growth, as we know, but we've actually, the result of that is that we've actually, but a fairly long period between 1990 and 2010 or so, not doing an awful lot with parallel computing, just speeding up the sequential stuff using this technology advances. And a lot of the other architectural techniques that have been used over that period have been known for donkey's years. They're more stuff from the 1960s. One of the machines in the IBM 360 family was a superscalar machine with out-of-order execution, multiple execution units, and the works. You can go and look it up in the IBM Journal of Research and Development from about 1967 or 8, as far as I remember. 360 Model 91. Not enormously successful. It was actually overcome fairly quickly by rather simpler versions of the architecture, which used caches as opposed to simple memory organization. So that's one thing that's been going on. Now, something. Is this going to move? Hello. It's stuck. Oh, thank you. Okay. And I've been reflecting on what's been going on at the moment, because obviously the post-2005, the Moore's Law thing got rather more problematic. It didn't just keep on speeding everything up. And actually, I suspect that the efficiency of the processors has not been doing very well, as opposed to the speed. The problem is that as you add additional execution units, as we do, you end up with a permanent overhead, and it doesn't always buy you very much performance. In a recent discussion with the originators of the ARM technology, we were looking at the efficiency of their M0. And Mike Muller made the comment that it looked as if the M0 was more efficient than anything they've made over the last 15 or 20 years. And that's because it's very similar to the original design. Very lean, mean, lightweight execution unit. That doesn't mean there's necessarily anything wrong with sticking deep pipelines and superscalar execution in if you want more performance. It just means that if you're trying to get energy efficiency and stuff, it may not be the right thing to do. And I can see I've now created some controversy, which is fine. I can't back this up. So I'd love somebody to produce the numbers to demonstrate this. The only ones I have are the work that I saw based on the M0. What I do know is that it is extremely difficult to keep a superscalar execution unit very busy. Once you get to 3 or 4 execution units, that's a real challenge. But, okay, 2.5-fold parallelism is on sequential software is doing reasonably well. So the rest is simply going to be an overhead a lot of the time. Now, of course, the other thing that's happened as a result of all this is that most systems have multiple processors. Even your telephone and everything has got more than one in these days. And it's pretty obvious one reason for that is back to the I/O problem. The superscalar applications processor with all its baggage to make it go fast, and the deep pipelines isn't very good at input-output. So you have to surround them with I/O processors, which are maybe the same architecture optimized differently, which is what's happening in the ARM processors in phones and things, or it could be different processors. So you've got to add these additional I/O processors, just like people did in the 1960s. And then the other issue is if you actually want more processing performance, the only way to do it is to add more. And then the question is, what kind? Do you add more of the same, or do you add something different? Well, the obvious place where you potentially add more is in graphics. There's an insatiable appetite for computer graphics. There hasn't been since that original machine back in the 1960s and 70s, and it hasn't stopped. It's become a technology driver almost. And it can use a lot of processors. We've known that for a long time. And it probably does make some sense to design application-specific graphics hardware, especially if it's replaced every year. It used to be a challenge to design graphics processors, and there were some spectacular failures back in the 70s and 80s, 80s in particular. I think there was one or two designs for very sophisticated wireframe graphics processing, and over the 2 or 3 years it took to design them, the world moved on to raster scan graphics, so they became obsolete. So you've got to be able to turn the design fairly quickly to keep up. But on the other hand, given that so many people seem to replace their phone every year, I guess you can just keep up and keep on optimizing for the next generation of software and try and get the best performance by implementing the algorithms and stuff in hardware. And of course, graphics processors are also applicable in some other areas. And high-performance computing is one of the ones that people have tried to target these gadgets at, for one or two reasons. Of course, there are two sides of high-performance computing. One of them is that we're trying to maximize the peak flops, performance the manufacturer guarantees you can't exceed. And it's really the top 500 list that matters more than what the flops were actually used for. Okay. On the other hand, more seriously, there are a few data parallel HPC applications which can use the same kind of technology that's used in computer graphics. I guess there's a reason behind that, because actually both graphics and high-performance computing are often involved in building models of the real world. So you'd expect to see some overlap between the algorithms that are used in those two application areas. Of course, as I've said many times before, including the last time I talked at this conference, in my view, the general purpose processing, especially parallel processing, it's the general purpose processing, not the specialized accelerators, and the way they're interconnected is what really affects performance and efficiency. It's not surprising that virtually all of these machines that have been built over the years have got somewhere a fairly powerful general purpose sequential processor tucked in the corner. It's the get out of jail free card. When the accelerator won't do the job because the application doesn't fit properly, that's the way you can still get the machine to perform well. And that's precisely why Cray, of course, had the sense to make sure his main processor was able to do high-performance sequential processing. So anyway, the general purpose processing of the wiring is what affects performance and efficiency, along with languages, tools, and algorithms. An area which seems to me to be not in brilliant shape right now. Let's have a look. What's mine done? Yeah, so this has been a gap for a long, long time. We still don't seem to have any particular sort of approach that gives us a suitable general purpose architectural framework around which you can build parallel machines, and languages are in the same boat, basically. We actually still have a variety of special purpose architectures and special purpose programming languages. It is actually, of course, always possible to execute parallel programming on sequential processes, but the converse isn't true. So we can't parallelize easily. So what you really want to be able to do is to write portable, reusable parallel software and then implement it on as many or as few cores as you actually want. As I said, in 1990, there was a lack of standardization. In 2012 and 13, there's a lack of standardization. I'm not quite sure why. When I was trying to understand this many years ago in the parallel computing community, we had a whole army of small companies doing high-performance computing, parallel computing. They were, in many cases, trying to sell the technology on the back of the fact that their languages and tools were better than the next guys. But users don't want to know that all the languages and tools are different. They want them all to be the same. At that time, actually, I will just read you this. I was very amused because I happened to drop into the Bristol Museum and noticed a little pamphlet that's still there, I think, called Electricity in Bristol, 1863 to 1948. It goes like this. There were too many small undertakings, little cooperation between them, and a multiplicity of different voltages, frequencies, and systems. In 1919, the Electricity Supply Act took a tentative step to establishing a national rather than a local system of electricity generation. How tentative it was is shown by the fact the commissioners did not have the power to compel undertakings to group themselves into joint electricity authorities. The Act left this to voluntary action. Such action was rarely forthcoming. No regional authority emerged. Parochialism triumphed over common sense. It always does. Well, so, now, of course, the solution to this was the whole lot was nationalized. And that sorted out the voltage and frequencies. So maybe you want a national initiative to have a standard programming language. Dare I say it? A Euro initiative, that's the one. That's the one. Okay. Well, what are we trying to do? Why do I say this is important, this generality? The thing is that there are not a huge number, but there are quite a lot of different ways we program parallel applications. And I want to be able to use any of them. Programming is difficult enough without being restricted to particular patterns of communication and so on. Some of these have been around for donkey's years. The parallel random access machines were around. We know how to implement those. Data parallelism is what your graphics processors and things tend to do with some of the supercomputing accelerators. Then there's the data flow graphs, which tend to be kind of graphics pipeline things. Task farms and server farms turn up in the server infrastructure. And of course, there's I/O and event handling and so on. And as these things should be embedded in a programming language, I'd expect to be able to use them in combination. There's nothing particularly radical about that, it seems to me. I mean, you know, in sequential computing, for many, many years, we've put together a few ideas, procedure calls, loops, conditionals, and so on and so on. We just expect to be able to use them freely. This is the same deal. Okay. And of course, the issue is that the SIMD stuff is basically, the single instruction multiple data things is doing data parallelism for you, but nothing much else. And this debate has been going on for a long time. It's sort of almost a religious debate was going on in the 1980s about whether you should build things SIMD or MIMD, and it's more or less the same debate even now. The argument sort of says that SIMD you can cram more and more, a lot of processes into a very small space because you don't have to bother with getting them to do instruction execution and so on. So you get very high density of computation. Actually, I didn't believe this was right in the 1980s, and I still don't. The actual cost of instruction handling to turn the simple processing unit into a thing that can execute instructions is very low if it's done properly. It takes a handful of instructions to actually make the thing into a general purpose processor. The benefit of doing that is that all the execution and synchronization of the system is done locally between pairs of processing agents and with the execution within the processing agent, and it avoids global communication. And as we know, global communication is expensive. So I think that MIMD arrays would run faster and at lower energy than SIMD ones. Okay. Again, that's an exercise for the reader to sort of try and prove it, okay, or prove the opposite. And the other point is that actually the MIMD thing, of course, can emulate the SIMD, but the converse doesn't work. You can't take an algorithm that's designed to run on a multiple instruction, multiple data machine and just mount it easily on a SIMD machine, unless you're very lucky. As far as the issue of unifying various of the key components here, computation, communication, synchronization, event handling, this is the only sales pitch for XMOS on this set of slides. We've already shown how to do that. Okay. The principle is there. You can actually basically build machines which can mount SIMD and various of those other patterns on probably without too much trouble these days. Some comments about why this is a good idea. If you want heterogeneity, you really want an implementation, not the architecture, as I've said before. Programming is made very complicated by multiple tool chains and languages and arbitrary architectural restrictions, like suddenly discovering that one large chunk of your machine will only run a particular kind of parallel structure, like a data parallelism. So we really want one programming model and lots of optimizations. Unless you're optimizing chips for specific application areas, you don't know what the ratio between the components should be. And so you're then stuck with the problem of potentially needing a range of them. Okay. It doesn't matter particularly if you're actually trying to make a specific machine to run a specific program. It's when you want to change the programs that the trouble starts. Okay. I mean, once you've made the chip, the distribution of the resources is fixed. It's almost an application-specific processor. If a new algorithm is needed, then there'll be some loss of efficiency, or you'll need a different chip. But of course, this is silly because the algorithms and the optimization and the evolution of the algorithms is what matters. They have a vastly bigger impact on performance and efficiency than almost anything you do in the hardware. Better algorithms are the solution to almost everything, certainly energy efficiency. So I think there are a few things that have gone wrong over the last few years. Firstly, I think general purpose parallel computers should be around and they should be programmable and reprogrammable by normal people. Not specialists, just like general purpose sequential programs are. I'm baffled about what's happened to software. It was supposed to be portable when I was young. Why do we install specific cores to run specific bits of software? This is odd, but we do. I mean, you know, that's why these specific application processes are being embedded. And of course, as the systems scale up, if you're going to have to put specific cores in to run specific blocks of software, then you're certainly going to get heterogeneity. It's not going to be very easy to manage, but there we are. Of course, we have this phenomenon that big market volumes have supported this Moore's law investment, and that's enabled growth of everything, especially complexity. So that's the underpinning issue here, that you've got a very large market supporting investments in very specific areas, like graphics and so on. And then we've had another thing that's gone wrong with parallelism is these persistent ideas that everything should be done with cache coherent shared memory, which I think I talked about last time. I gave a talk here. I'm not a fan of shared memory. I think it's extremely hard to use. I don't see why people think that this is a solution to anything. And it also, it's resulting in some very strange devices being constructed, where you find that all that's been installed as a communication medium between the processes is cache-coherent shared memory, and then somebody builds a message passing layer on top of it. And then somebody builds a memory abstraction on top of the message passing layer. I'm not kidding. And we seem to have got into this thing of design by aggregation, as I call it. I think it started in software design, but it's certainly spreading into hardware design. You take big chunks of software from libraries and stick them together. You don't look inside the box to see what's going on. Abstraction, in my view, is supposed to be about managing complexity, not hiding it, but some people seem to think the opposite. And you've got this problem that nobody wants to risk redesigning these complex subcomponents or porting complex software around. So it is an ultimate lock-in. Okay? Too big to understand, too big to fail. I think we've heard that somewhere else. So is there an alternative? Well, yes, of course there is. We've known how to do this kind of homogeneous parallel computing for a long time. The issue, as I've said before, is the interconnect. We don't want heterogeneity here. We want known scalable properties, bounded predictable latencies. I think you should build things on top of message passing. It's the way the world works, and it's easy to understand. The process just has to be designed to keep up with the interconnect, and that doesn't need a lot of complication. If necessary, run them slower and put more in. Once you've got to the scale of having tens or hundreds of processes, it really doesn't matter if you have twice as many at half the speed. I don't think it really matters that much if there's some heterogeneity in the details of the processor architectures, but I'm not sure it's really worth it apart from one or two of these areas like I/O. There isn't a big performance factor in the details of an architecture. I hate to say that, having spent a long time working on things like this, but factors of 2 or 3 are probably all you normally get. I've mentioned interconnection, and in particular, I'm dismayed to see the number of two-dimensional meshes appearing in chips these days. We knew that two-dimensional meshes were a bad idea from the point of view of mounting software in 1990. People were attempting to move towards things like factories and closed networks and things because they provide the connectivity that's needed to support the applications. Oddly enough, the communications industry, of course, uses the networks we should be using for computing. And we seem to have adopted something quite different. I think people just assume that silicon is sort of two-dimensional, and so you should obviously take arrays of tile the chip to produce the mesh network. But of course, all you get is massive hotspots in the middle of the chip. That's why you want it, of course. You need the low latency to do high parallelism and to use the usual techniques of latency hiding. Okay. We know that we can use collections of processes with suitable interconnects and stuff to execute anything, including large sequential programs. And so the general philosophy should be to design the interconnection system first to deliver the throughput, and then you can just add the process on to keep it busy. It's the opposite way around to the way people tend to work. They tend to design enough compute performance in and then stick in some wiring to make them communicate back to front. It is a thing I've observed over the years that actually as architects get older, they start off when they're young designing CPUs, and then when they get older, they start designing interconnect first. That's how the IBM channel came into existence. The architectural structure of the machine was designed before they worried too much about the details of all the components that were being fitted together. So this is my notion of universality. It's not mine, actually. It's the one that we had many years ago. But the key point is universal processors we've had for a long time. The new one is universal interconnect. And what I mean by that is stuff that will implement any of the patterns of communication that people will dream up whilst they're trying to design programs. And for that, you want to give people complete freedom. Okay. And there are various techniques we can use to do this and to optimize the particular programming styles to fit on those machines. And there is a potential sort of emulation overhead, as you call it, as you apply this universal structure to things that could otherwise be specialized, but it's normally hideable by this a sufficient amount of excess parallelism, as it's called, in the application. And I think we should be trying to build processing like memory. DRAM memories, they're just built by choosing an economic chip size, 70 square millimeters typically, and then you just stack them up in packages in order to produce what people want to buy on the street. And processing should be exactly the same. Okay? I think for logic it will be about 100 square millimeters. That will hold a lot of processors. You should these days be able to think about, just like the DRAM people, stacking them up in 3D. And if you really want to connect more of those chips together, then there's one or two of these interesting technologies coming along to help you to do it. So those are little sort of components, potentially, all the behavior defined by software, completely homogeneous. See, I'm advertising heterogeneous architectures. Okay. So here we are. Here's my optimistic view of the future. Okay. I keep hoping that the new generation is getting bored with more and more graphics. Reality is more interesting. The Internet of Things and robots and stuff, where my interests are these days. I think we really should realize we shouldn't be throwing away 1 billion phones a year. That market we've generated for more and more and more and more and more slightly better graphics stuff is not really sustainable, I don't think. I hope not anyway. Where are they, by the way? Have you all got a drawer full like I have? Some of the materials in those things are very difficult to recycle and they're scarce because the gold of everything has been dispersed so thinly across the planet's mobile phones that collecting it back again will be tricky. I think general purpose parallelism will emerge. I think it is doing anyway. I think actually, although I commented a lot about graphics, I think actually many of the people that are working in that area have now realized that the graphics pipeline is quite complicated and diverse, and it actually requires far more than SIMD processing to do it properly. So I think the graphics stuff anyway will move towards much more general purpose parallelism. Certainly the super high performance computer will have to. Because the applications are too important and diverse to be simply delivered by data parallelism stuff. I think as that happens, it will cause some surprises. I think it will enable some new applications and products. There will still be heterogeneity in the interfaces, especially in areas like robotics, on-the-body gadgets and stuff. And I think there may be some interesting new places for heterogeneity. I mean, I have some friends who do quantum computing. When you ask how they're going to run the quantum computer, the answer is they're going to put a classical on alongside it to control it. Of course. Right, well, I just ended up telling you about a couple of projects that I've got on the go. One of them is how simple can you make a parallel processor? I have a design for a very simple processing node and network to go along with it, and programming languages and stuff. There was a motivation for this, which is just because I like building simple things, but it's got a little more momentum recently because I'm struggling now to work out how to actually educate the next generation about how computers work, and having a very simple processor would be a good start. You should try explaining to first-year students how modern processors work. We were foolish enough to actually try and adopt a version of the ARM. And I extracted about 30 instructions from the thumb instruction set and wrote a compiler for them, which is all very neat. What we forgot to do was to actually produce a nice programming language manual for just the 30 instructions. And so the students started burrowing amongst ARM's manuals, all 1,000 pages of it, and got rather confused. Okay. So if ARM, by the way, would like a decent subset of the ARM thumb, it's on my website. It's about 30-odd instructions, and it will do most of the things you want to do. And it can be documented in a couple of pages. So anyway, so this is one of the things that's now motivating me. Actually, we're going to build an implementation of this thing, which can be laid out on the bench. Okay? Because unless you explode the computer into its component parts, its control logic, its data parts, and so on, nobody can understand how it works anymore. None of the teenagers have ever seen a piece of mechanized computing. They don't have slide rules, they don't have hand-crank calculators or anything, so you have to really take it all apart for them. So that's what we're doing. And I'm hoping I can do this cheaply enough to get it into the schools. And actually, if I can get parallel computing into the schools, that would be a great achievement, because then we wouldn't get all these kids thinking the world is sequential. The 10-year-olds don't, you see. My colleagues, one of my colleagues commented that her 10-year-old had said, "Why can't my robot sing and dance at the same time?" Interesting. And of course, nothing hidden by abstraction layers. And the next project, which I'm going to tell you about, this is the last slide. 2014 will be the 30th anniversary of the launch of the Transfuture and Optum. And one or two people think it would be great to reconstruct it. We could do a retro version, maybe. It would be really also good to do a 2014 version. I think it might be really fast. It's very, very small. And when I say a chip 2000 could hold thousands, when I did the calculation, that square centimetre of silicon would hold about 4,000 transfuses of the kind we shipped in 1984. Okay. You might decide to trade off a bit of that. It only had 2 kilobytes of memory on chip, so you might want a bit more memory, so you might want to do that trade-off. But the other question is, how fast would it go? Difficult to see why it wouldn't go very fast, actually. It's only got a handful of registers and a very simple control structure. So it might be an interesting gadget. If you'd like to help with that, get in touch. And at the very least, this looks like a good excuse for a party.
So we do have time for just one question. Is there any questions in the audience from David's talk? Yeah, hang on, just.
So, do you still think that Occam is a good language for this kind of problem?
I think, well, what can I say about Occam? I think it's a substantial improvement on most of its successors. to quote Tony Hall talking about alcohol. I mean, there are some things that I think you might do differently, and I think one of the things we've been experimenting with recently is languages designed for very large numbers of processors. There were some things that are quite fiddly in Occam when you get to large numbers. Describing the interconnection structures, they weren't always very transparent because you ended up with large arrays of channels and things and complicated subscripts rather than being able to see what the connectivity was. And I think that can be done better. Another thought that I've had recently, I struggle with why people find parallel programming, seem to find it difficult, and you can see some reasons, but I think part of the problem, the difference is that when you're actually writing a sequential program, you're more or less telling a story, and we're quite good at telling stories. It's a sort of sequential, but this is why sequential stuff is easy, I think. Whereas doing a parallel thing, you more or less got to conceptualize some kind of structure and put it there. So I think they're quite different intellectual activities in some ways. There are some interesting intermediate points, however. So if you build up a parallel program, effectively almost sequentially by putting layer after layer of servers or something on top of each other, then it's closer to sequential programming. So I think that once we've got this thing and your mental model of the machine is a massive sea of processors, and you're sitting in one corner of it, and every time you do something, you throw a task off and it starts running. That's quite an interesting way of building up the functionality that you're doing. Which gets somewhere halfway between parallel and sequential. So I think there's some interesting challenges here. There isn't all that much going on as far as I can see, though. There's various attempts to build these things. Quite a lot of stuff I'm very surprised to see has not been picked up. I mean, Occam it wasn't just the parallelism; it's the fact that it was done safely. Okay? I found myself in a conference a couple of years ago in the States, which was billed as a deterministic parallel programming workshop. And I naively, until a week or two before this event, thought it was about deterministic in the sense of time deterministic, sort of predictable timing, like I do at Xmas for I/O and stuff. I got there and discovered it was actually about just getting the right answer. Because effectively they were just using shared variable programming and trying to make it safe by some piece of magic. Okay? I think this is really, really weird. I mean, the Occam thing really worked from the point of view of making it possible for people to write programs and know that they were going to work predictably. The race conditions are gone. It had a very safe model for error containment that made it relatively easy to build resilient systems. A lot of things in the language design, some of which have been reused and adopted. So I think we did quite a good job, but I think there are things more things could do now.
Thank you. Thank you very much, David. Thank you.